In this podcast, we'll be trying to understand how neutrinos are detected. But firstly, let us answer the question, what are neutrinos? Neutrinos are abundant fundamental particles that are produced by the decay of radioactive elements and nuclear reactions of stars. Under the standard model, described as leptons, there stands three different types of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These chargeless neutrinos are notoriously hard to detect. They only interact by the weak nuclear force and gravity. However, in the standard model, neutrinos are treated as massless particles, like photons or gravitons. Yet these particles undergo a phenomenon known as neutrino oscillation. To put it simply, a neutrino created with a specific lepton flavor can be measured later to have a different flavor. It's suggested that neutrinos have a non-zero mass, and that the mass cannot be identical for all three different flavors. The 2015 Physics Nobel Prize went to the work in discovering neutrino oscillations experimentally. Does this mean that the standard model is not an accurate model? All we can know for now is that it provides a basic but incomplete picture of what exists in the universe. Though neutrinos seldom react with other particles, this does not mean they do not. A neutrino could react by being scattered off a neutron, producing a proton and a charged lepton. This interaction can be observed, but requires thousands of tons of target material during experiments. Another interaction occurs when the neutrino is scattered off an electron. So how do we detect particles that are capable of passing through the Earth without interacting? The famous Super Kamiokande detector in Japan is buried 1,000 meters underground and uses 50,000 tons of water. It is surrounded by photomultiplier tubes measuring the amount of Cherenkov radiation, an electromagnetic radiation that gives underwater nuclear reactions that characteristic blue glow. Other observatories use chlorine, ice, or heavy water, depending on the type of reaction they can measure. What are the motivations for scientific interest in neutrinos? Supernova explosions releases most of the radiant energy in a huge burst of neutrinos traveling close to the speed of light, and therefore neutrinos are very useful in detection and the study of a collapsing star. Features such as weak interaction with other particles means that it can probe further than other radiation. It was proposed to be used to detect the sun's core conditions, as electromagnetic waves were diffused by the density and the volume of the matter surrounding the core. Within the span of 2 years, the Ice Cube Neutrino Observatory located in the South Pole detected 28 neutrinos that are thought to have originated outside the solar system. This long-range particle could be our way of observing the universe beyond the Milky Way.
Created using Powtoon.